All right.
Okay, give me a sec.
I started recording. Don't say anything incriminating.
Okay.
All right. Okay, so welcome to the last yap. So here's the deal. I'm doing columns. Let me just turn my phone on silent. Yeah, we're doing columns, and then we're just gonna do the first two topics here. So short columns, and then they outline what deficit plastic centroid is, and then the interaction diagram, and that's like if you get a column question in your finals, it'll be an interaction diagram question, and then the design of short columns isn't in the course anymore. So yeah, I don't know if that's a word for it, not in the course anymore, but it's not expected in your finals because it's really aids. That's like when you have to like size the column and like determine how much steel and stuff you need inside of it. It's like interaction diagrams more about like determining what the capacity is given that you have like constants for the geometry and the steel and stuff in it. Alright, so we're gonna run over what like a column is compared to a beam. So here I've drawn like a frame where we have, I don't know, it's like a simple 2D frame where we have two columns and then the beam. And yeah, we can consider this kind of like semi-rigid connection between the columns and the beams. And that's what we usually do when we do our beam design, right? So we have like our flexure checks, our shear checks, serviceability, all that stuff. We have like the distributed loads acting on the beam, mostly due to like weight, self-weight, and live loading and stuff like that. But for columns, it's slightly different. So we consider axial forces. We consider compression. That's the word. So P is compression and M is the moments. So that's from the semi-rigid connection. Sometimes you have a bending moment applied on the beam. And compression comes from like those dead loads and live loads and stuff like that. Or like gravity loads, I guess. But yeah, hopefully that makes sense. I feel like that one's not too bad to understand. All right, so the next thing you have to understand is slenderness ratio. So, actually, you don't need to understand this. This is all background knowledge still. But slenderness ratio is the ratio between the length and the least dimension. So for a cross section, we have B, the width, and D, the depth, right? The least dimension is what we call the smaller out of these two things, right? So generally the width is denoted by B, and here we just call B the least dimension, right? So the slenderness ratio is the ratio between the total length of that column and B. And if that's less than 12, that's considered a short column, right? And then if it's greater than 12, that ratio, that's considered a slender column. So we focus on short columns in this course, which is actually a good thing because short columns have less, they're less difficult, I guess. Not that the topic in general is easy, but like when you have slender members, they're prone to buckling, and then there's a lot of issues to do with like, local buckling, global buckling. It's just generally quite complicated. But buckling effects don't happen when you have short columns, essentially, right? If you remember Dom from Steels, basically like compression and flexure, you have to do buckling checks for steel structures, right?
Yeah, that's ace.
It is. But luckily, and one of the reasons I prefer concrete, there's no buckling involved. You can think of the failure that happens on a short column as like a material failure. So it's like the kind of failure you'd expect based on the material properties. But buckling failure overrides it if the geometry is too slender. So it's like a unexpected failure, I guess you can call it. All right. So we have two types of columns that we talk about in general. Tide columns and spiral columns, right? We're going to focus on tide columns in this course. They look almost like beams, but you can imagine they're like vertical, so they have like these shear bars that they basically prevent buckling, right? They prevent the beam the column from buckling, and they have like the steel laid out in like a grid, like a rectangle, and the overall shape is like rectangular, right? Whereas we can also imagine spiral columns, which have like the axial bars laid out as such, and then they almost have like this spring-like shape. And this spring is actually stronger than the shear bars for a tied column, but they're much harder to design, so this out of the scope of this course. The springs are like, yeah, and also they have to be like custom manufactured in like by like the steel manufacturer for the specific size of the column and stuff like that. So they're very expensive. I guess like, yeah, they're very expensive in design. Okay, anyway. Oh yeah, but it behaves like a spring. You can literally imagine it like compressing, and it bounces the forces back up, kind of thing. Anyway, yeah, and it also acts as the shear reinforcement as well. Okay, so the first thing we're actually going to talk about is depth to the plastic centroid. So this is a bit of a trippy thing to wrap your head around. Basically, it's to do with compression, right? So in the columns part of this course, you have to consider the case of pure compression, unlike before for beams where we just consider flexure, right? So this strain diagram used to be like triangular, I guess you can say, and where like the top was compression, and then that bottom triangle was tension, right? So the definition of PC, or depth to the PC, plastic centroid, comes from the pure compression case. Okay, so it's basically the centroid of the resisting axial forces of the section if the concrete is compressed to its maximum allowable stress, and the steel is compressed to the yield stress with a uniform strain. So in other words, it's where the equivalent point load would be. So here I've drawn it in purple. It's where the equivalent point load would be for all these stresses, like where this would be applied for like all these stresses and forces to be like one massive force, I guess, right? That makes sense. I'll take a sip of my water. All right. So who's in this call right now? Oh shit, we got like Gina. Okay, we got a couple people. All right, so I'm gonna need some guessing from people, basically, right? So basically, the first thing to note is that the entire strain profile is in compression, but what point are we referring to? Because this is quite important, right? Like what strain point are we referring to when we consider the failure in pure compression?
Is it neutral axis?
You're on the right track, but what do you mean?
I don't know how to elaborate.
Okay, well, I'll give you a hint. So, like, you know how before we had this triangle for flexure?
Yeah.
You're talking about this, right? Then, which before was the neutral axis.
Yeah.
And where the strain was 0 is where the neutral axis sat, right?
Yeah.
So I think I know what you're talking about, but we actually don't have a neutral axis for pure compression. The line that I've drawn is the plastic centroid line, so we actually don't have this at all.
Okay.
But what was the other critical value on this strain diagram from the previous case? If anyone remembers.
I'm gonna guess the map. Sorry.
Basically, concrete, right? For concrete to fail, the compression, for reinforced concrete to fail, the maximum, the ultimate, compressive fiber has to reach 0.003. That's the definition for all failure modes, including bending when we had this, right? And this was 0.003, if you remember this number. And now, same thing for uniform compression, right? So once we've reached this point, we make a few assumptions. The first is that this both the steel has yielded. I've got another question. I'm really sorry. I'm gonna have to pick on people because I don't know. It's just harder in like online than in person to get people to participate. Wilson, do you wanna have a guess at this question? So, which of the bars are tensile in this case, and which are compressive bars?
The top is. Didn't you say the concrete was all in compression?
Yep.
Is the steel all in compression as well?
You're right. Very good. You've dodged my trick question. So these are both compressive bars because the whole thing's in compression. But we know that the material properties of steel look like this. They're uniform in compression and tension, right? So yeah, because that yield strength is the same, we're going to consider it the same number in compression and tension anyway. So yeah, but yeah, this will be usually 500 MPa for both of these for the stress amount, and then you multiply that by the area to get the force, right? Okay, here's the other thing. Sorry, I'm gonna have to pick on more people. Arjuna, previously, what was this amount for a rectangular stress block, if you remember?
I do not remember.
Previously, it was alpha 2 F-C, right? Does that ring a bell?
Not gonna lie, not really.
Okay, I like it.
Sorry.
Basically, previously we had bending, right? Where you had the rectangular stress block that looks like this. This amount was gamma dn, right?
Yeah.
And this was alpha 2 FC, right?
Okay.
So I've got a new variable to introduce to you. It's alpha 1, right? Alpha 1 is only used for the case of pure compression. I'll show you the formula for it later. But we use this and not alpha 2 for our case of pure compression. And that's what we use here. And we do that, and then the entire thing, it's not gamma dn because we don't have a neutral axis, and the entire concrete block is in compression, so that's just d, right? And then multiplied by the width, and that gives us the force of the compressive concrete, right? Okay, so here's the formula for alpha 1, right? I haven't memorized this, right? This formula, because it doesn't come up very often. It looks a little different. It's 1 minus 0.003 FC, but alpha 1 has to be less than 0.85, but greater than 0.72, right? So that's the fall between this range. Okay. Other things to note, AG refers to the area of concrete, AS refers to the area of steel. Here I've called it the area of the tensile bars and compressive bars, but Wilson was right. They're actually both in compression, but the only reason I've called them the tensile bars is because later on they will become tensile bars when we're referring to like bending and stuff. Okay. Let's find DPC. So DPC, as we mentioned, was the depth to this line, right? Oh, sorry, I'm drawing here. So it's the depth from the compressive fiber to this line, which we call the plastic centroid, right? And in order to find this, we have to sum the moments, right? So if you remember moments, right? Moments is equal to the force times the lever arm, right? Lever arm. And so basically we look at our force diagram. Okay, well, let's look at the left-hand side. The left-hand side is NEO multiplied by DPC. So that's that purple force multiplied by that red line. the right-hand side is everything here. So we have, let's do the concrete first. The concrete, the lever arm is half of the depth, right? So force of the concrete, half of the depth, plus for the compressor bars, that's this one, and the depth we call it, DS1, DS2. I've called it the other way around, so I'm going to change this. Oops. S2, S1, right? Okay, anyway. Yeah. And then, we basically just divide out what we found for the axial force in order to find DPC, right? So we were looking for this, and we solved for this in the last step. We divide this out in order to find, the answer for DPC. So DPC is used later on, actually, for other calculations. So it's quite important to find this as our first step when we're doing columns. Okay. Who have I not asked the question? I think Farhan, right? Actually, no, I won't ask this question. It's a bit of a stitch-up question. Basically, sometimes you can expect voids in the concrete. Okay. Oh, actually, I might ask this to Farhan. You might be able to get it, but it's like kind of a hard question. If we have a void in the concrete, right, and the area of the force due to the concrete was this, what should we do in order to account for the void in the concrete? In terms of its forces. Maybe I'll show you up here.
So this is a void in the concrete.
Yep. Just like a hole.
Yep.
Actually, I'll show you on the diagram below because it's more like an equation.
So what's the question? The eighth is a void in the concrete.
Yeah, what would we do with this formula? So basically, here on the right-hand side of our formula, we've done each of the forces multiplied by the lever arm, right? And so for the concrete component, that's this, right? What would we do to account for this void in the concrete if there was one?
Don't need to do anything.
Fuck it. No, but the problem is if we don't do anything, our assumption would be wrong for where the centroid of the concrete is, right? It wouldn't be depth over 2.
Oh yeah, that's true.
But instead of fucking finding the Y centroid, you know, all that shit, you can actually do this instead. You can pretend that that void is its own force. And it sounds cooked, right? But it makes sense. But we subtract it, aka it goes in the other direction. Sorry. So this is alpha 1 FC, but now we're doing the area of the void. Do you see how the arrow points in the other direction? And so we actually subtract this. Right, so that's actually the force of the void, I guess, right? But we also have to do the lever arm, which is the depth to the void, so the depth to the middle of the void. And when we multiply it by that, now we have the moments due to that void. Yeah. Anyway, that's what I said here in this little comment. Okay. Let's move on to the interaction diagram. Okay, basically there's a few things happening here. The first one is that this is the axial forces axis, right? Where here is compression. Here's the case of pure compression. And here's the case of pure tension, right? So we know concrete's not very good in tension. Reinforced concrete's not very good in tension. So it would be around here. Whereas it's much better in compression. But we have all these other cases which involve bending moments, right? There's a case here where we don't have any axial forces, right? And that's because we don't have any axial forces, and then this is in pure bending. So this is actually the case we use for... It's solved very similarly to how we solve a beam. Because for a beam, we don't have any axial forces, right? And so we use all the same methods. We use rectangular stress block and all that stuff, right? In order to solve for its ultimate moment capacity. All right, Dom, I've got a hard one for you. How come... Because for most materials, the interaction diagram looks something like this. Maybe like, it's actually usually even, but let's just say it looks roughly in that shape, right? How come concrete does this?
It's going to have to do with the tradie thing.
Sort of. It's a bit of a hard question, but like, why do you reckon when you combine compression and bending, that reinforced concrete actually has like almost like a higher capacity? So by the way, this is the failure envelope. So everything out here causes the concrete to fail. Everything inside means that the concrete is still standing. So why does this envelope kind of come out when you apply axial forces to it, rather than it just being in pure bending? Do you know what I mean? So the bending strength actually increases when you apply compression to it.
I don't know. Does it have to do with the steel being squished? Does that make it stronger in some other direction?
Kind of, but it's more about the concrete. You're thinking about the steel, right?
Yeah.
What properties do we know about concrete?
I don't know.
Well, we know concrete's
Right.
we know concrete's bad in tension, right?
Yeah.
And so when we have pure bending, here's what happens. Here's our neutral axis, something in the ultimate moment, right? And then we have the strain that looks like this, all that stuff, right? And then we have a rectangular stress block to represent the concrete, all that stuff, right? And then the steel rebar, and this is the compressor bars, right? However, concrete is completely useless from here.
Yep.
Because it's in tension. But if we actually push down on the concrete while bending it, it almost buffs the concrete strength because more of it is in compression, right?
Oh, so then the neutral axis is lower, so it's more effective.
Yeah. Actually, that's true. Yeah, basically.
Okay.
But yeah, it's kind of interesting. It's like a property of this only applies to concrete.
Okay.
The material. But yeah, anyway, so we're going to analyze these points: decompression point, balance point. These are the kind of harder ones to understand because it does have some of those things happening, like having axial forces and bending at the same time. Having compression and bending at the same time. All right, so we already talked about pure compression, but just a summary from what I was talking about, what I was yapping about before. First, you have to find the compression, right? So you do the sum of the forces, because you need to find the depth to the plastic centroid. That's required for the next few steps. Well, it's not required, but it does make the next few steps a lot easier if you do that, right? So that's step 2. But you need NUO to find DPC. Okay, now we're getting into those kind of more complicated points where we have axial force. Oh, we have compression and bending at the same time, right? So this next point is called the decompression point, and it's where the tensile steel is 0 force, right? Okay, so to understand what's happening here, we have 2 lines. One is the neutral axis, and one is the depth to the plastic centroid, right? Okay, Wilson, I've got a question for you, man. So normally the neutral axis is way up here, right? And then the strain strain diagram will look different. So what would the strain diagram look like for the case that we're talking about right now, where the neutral axis is way down here?
Is it is it like usually it's more in tensile and less in compression, and now it's more in compression
Yes.
than
Basically.
tensile?
So how would you describe where the strain is 0?
At the DPC?
So you reckon it looks like this?
Yeah.
Kind of, but the DPC has nothing to do with the neutral axis.
Oh, this is just a big fat guess, but actually never mind.
No, what were you gonna say? I think you were on the right track.
It would just have a straight line down,
Like that?
something like that.
This is actually the
Yeah.
case of the first point. This is pure compression.
Okay.
But we actually have some bending action.
Decompression.
Decompression. Okay, well, a neutral axis is defined as the point of 0 strain, if that helps with where you reckon this will be.
Can you say that again?
The neutral
Neutral.
axis is defined as the point of 0 strain.
Oh. So it would just have a diagonal line down to the neutral axis?
Yep. It's like this.
Oh, okay.
What about this point?
What's-
What's this point?
That point is the maximum compression?
Which is compressive strain.
Which is what?
Oh, do you know do you remember what it is?
No.
It's always
0.003.
Very good, very good. Okay, here's what it looks like. This looks really unusual because again, normally our in pure bending it looks like this, yeah. We're just comparing it to pure bending, which is what we know. But it doesn't look like that, essentially, right? What's happening here is the neutral axis is the point of 0 strain, right? And it's at the tensile bar, right? Okay. Who's next? I think it was Arjuna. Okay. Oh, actually, wait. I want to ask you this yet. Well, I've only got hard questions left. Okay, sorry. So I'm gonna rotate through people, and give them hard questions. So
That's alright.
here, this is alpha 2 FC, right? So we're using alpha 2 again. So once we have bending action again, we use alpha 2, not F1. Sorry, not alpha 1. Alpha 1 is purely compression. And here we're going to use gamma dn. So this is a rectangular stress block. This is a really big rectangular stress block because more of the concrete is in compression. Okay. Arjuna, so what type of bars are these on the top side? Are they tensile or compressive?
Well, I think the top half is like above, like the neutral axis is still in tension.
No.
There's another one, compression.
Yeah. So remember, 0.003 is always on the compressive side. This number is the ultimate compressive strain, right? So therefore, these are the compressive bars. But I've got another follow-up question for you, right? Are these bars yielded? Like, this isn't a straightforward answer, but it's from your guess. Do you reckon these are yielded?
Like, given that they're
Yeah, they're being compressed. But yeah.
I don't know, but I'm gonna guess no.
You would be correct in thinking that normally, because if you think about pure bending, right? And then we have our bars here. That's our compressive bars normally, right? They're not very far from the neutral axis, right? So what the neutral axis is how far something's being pulled apart or compressed together, right? So here, the bars are being compressed, right? And the
Yeah.
tensile bars aren't being pulled at all because they're on the neutral axis. Whereas in our normal bending case, the tensile bars are being pulled a lot, and the compressive bars are only being pulled a little bit because they're not very far from the neutral axis, right?
Yeah.
So actually, in our normal case, we generally assume the compressive bars have not yielded. Okay, so you would be right in that assumption, but it's actually more likely that they have yielded in the case of decompression.
Okay.
Because they're really far away from the neutral axis. So how far this is to the neutral axis is actually what determines whether it's yielded or not.
Right.
Yep. Okay, who was next? Farhan. So for the forces diagram now, right? I'm just gonna say the compressive force is this. This is standard from our bending case, right? For the compressive strength of the concrete. And this is gamma dn on 2. For our compressive bars, how would we express their force? This is to Farhan, yeah.
For the compressive bars?
Yeah.
Isn't it just FSY times ASC?
Yes. Okay, now what about the tensile bars?
FSY times AST?
So, FSY is 500, right?
Yeah.
So this is when we have our bars fully yielded.
Yes.
If we use
Okay.
this, it assumes that it's less than 500.
Yeah.
Right. So is it more likely the tensile bars are, in this particular case, yielded or not yielded? Remember, it's about the how far away it is from the neutral axis.
Yeah. I would say not yielded.
You're correct, but we actually know exactly how much stress is on it without calculating it in this particular case. It's not only less than 500 MPa, it's a certain number. What do you think that is?
Equal to 500?
Oh, sorry. If it's equal to 500, then it's FSY, which means it's yielded.
Okay, that's true.
If it's less than 500, what do we think it is in this particular case of decompression? Gotcha.
In the case of decompression, it would be 15 MPa?
15, did you say?
Yeah.
No, not quite. Okay, what if I told you it's 0?
I would not believe you.
How much force the bars can take, or is currently taking, is about its strain. The strain is what activates the steel's force, right? So if our neutral axis is on where the tensile bars is, it means the tensile bars aren't contributing any force at all to the moments. Do you know what I mean?
Yeah.
So since the neutral axis is sitting exactly in the middle of our tensile layer, our steel force is considered to be 0 force. That's the definition of this point that we're referring to. That's Ku is equal to 1, and dn is actually dst. So you know how we normally calculate dn? We don't need to calculate dn because we know where dn is exactly based on our assumption beforehand. So I drew this arrow to kind of bait you, but this is 0 force. And then you take the moment equilibrium from there. Okay, but the thing is, what we do is we actually take... Oh, well, first of all, you need a... Okay, let me show you the graph again. We're solving for this point, right? Step 1 is solve this, right? And then step 2 is solve this. We need to solve for both the axial force and the moments, because both of them are non-zero in this stage. So in order to solve for the ultimate compressive force, you need to add together the compressive concrete and the compressive steel. But we don't have any tensile steel, so we don't need to consider that in this stage, right? And then the next thing we have to do is take the sum of the moments about the plastic centroid. So this is why it's important to have PC, because you have to take the sum of the moments about PC, and that's what allows you to find the ultimate moments. Oh, and I think I didn't talk about this in the notes actually, but there's this concept called eccentricity, and it's equal to the ultimate moment divided by the ultimate compressive force. Basically, it's about the offset in force. I don't know if I have a good explanation for this off the top of my head. Eccentricity is like the offset of this axial force based on the moments, I guess. That's not a great explanation. Fuck. Okay, whatever. I'll find a good explanation for that and then come back to you guys. But yeah. Okay, next we're going to talk about the balance point. This is the other one that's tricky to understand, alright? So this is where the concrete cracks and the tensile steel yields at the same time. Alright? Oh shit, who am I up to pick on? I'll come back to Dom, but I have to think of a good question. Oh fuck. Okay. Basically, if you look at our strain arrangement, it doesn't quite look like a normal case of bending, which is this. So it's a little bit further down. The triangle's a little bit further down. But yeah, we essentially know. We know what. Okay. Bear with me for a second as I think about how to explain this stage. All right. Okay. Let me just start with this. This is the stage where the concrete cracks, which is this, and the tensile steel yields, which is this, at the same time. All right. And so for both of these assumptions, our ductility turns out to be 0.545, right? Based on our case of 500 MPa steel with an elastic modulus of 200 GPa. All right. Okay. All right, Dom. Here's my question for you. In this stage, do you reckon? Oh, sorry. I've kind of. Okay, you know what? I'm fucking hiding these. Sorry. In this stage, are our compressive bars yielded and are our tensile bars yielded? Do you reckon?
The bottom one yielded.
Yes. And how do we know that for sure?
Vibes.
So in our normal case, right? We base it off of vibes, right? We say that this is our strain diagram, right?
Yeah.
What vibes causes this to yield? Like what is the thing about the strain diagram that causes this to yield? Let's say this particular point is a strain of the tensile bars, right?
Yeah.
What number does this have to be greater than in order to yield?
0.003.
Not quite. So you think it's 0.003, but it's actually this number, epsilon sy, right? Do you remember this? 500 MPa over 200,000 MPa. And have you seen this number, 0.0025?
Oh yeah.
That's the steel yield strain limit. So once your strain has crossed over that limit, then your steel has yielded.
Okay.
What we are saying in this particular point is that our steel yield strain is equal to our tensile bar strain.
Okay.
So how can you be sure that we have yielded bars?
Wait, can you say that previous thing you said?
The question or
No, you said how the. I can't remember. You said something steel is equal to something else.
yeah, the strain of the steel. Sorry, the strain
Yeah.
of the tensile steel is equal to the strain of the steel yield, right? Like
Yeah.
the limit.
So isn't it just when it's bigger than that?
Yeah, bigger or equal to, right?
Yeah.
But what do we know the number is? Like
Is it
basically,
just-
yeah. Basically, I'm trying to say like the definition of this whole point is this is exactly when the steel yields.
Yeah.
So it has to give you 500 MPa because we're exactly on the limit in this stage.
Oh, okay, yeah.
Yeah, that's why. So instead of like 0.1 milliseconds ago, we were on 49.95 stress, right? And we've
Yeah.
just hit the point, if we're increasing the stress slowly, of hitting 500 MPa.
Okay.
That's what defines the balance point.
Yeah.
And then what about the compressive steel? Do you reckon that's yielded or no?
I think it's not yielded.
That's a good guess. I would say it's not yielded, but you have to check because this is as ambiguous as it gets. It can be yielded or it cannot get yielded. It cannot be yielded because you don't know if dn is greater than the depth from the neutral axis to the steel or not. If these numbers are similar, it could either be yielded or not. Basically. Oh, sorry.
Okay.
Yeah. Okay. Yeah. So you should definitely check the compressive bar yield assumption in this stage. Anyway, so we have sigma CS, ACS, ASC. Sorry. FSY, AST. Right. Yeah. And then we need to find dn because dn is actually unknown in this stage, and we need it to solve for our moment equilibrium. Like that. Accounting for voids as well is quite aids. One thing to note is that in the finals, right? Actually no, jokes. Okay, no, that's the next stage. Sorry, I was thinking of something else. All right. So we are back to pure bending, right? So we actually don't need the depth to the plastic centroid for the case of pure bending because it only applies when you have axial forces, right? And in the case of pure bending, we don't have any axial forces. All right, Wilson, do you remember how you generally, like, what are the general steps to solving flexural capacity in like a beam? And this applies to columns as well.
A what capacity?
Wait, ultimate moment capacity. I was solving for MUO.
Oh. Is that the max moment? Are you asking for the max moment?
Yep. So how do we solve for that generally?
Is it the EI formula?
Oh,
Capital E, capital I, and then there's like a compressive pi or something.
no.
Oh.
I think that's buckling that you're thinking of. Yeah, I think that's buckling. Not quite. Wait, I don't know how like caught up you are with the course. I don't know if I should be asking this question to you or not.
I'm not very caught up. What was the question? Let me
The
try
question
one
is, how
more
do you
time.
solve for MUI generally for a beam? This is around week 5.
For a beam?
Yep.
Can you just find the reaction forces and da?
Are you talking about the forces in the internal forces in the beam?
No.
Okay, I think you're thinking about reaction
I'm not sure.
forces along a beam, right? The bending moment diagram. And then these are the reaction forces, right?
Yeah. That's what I was
That solves for this M star, right?
Oh, we're not finding M star.
We're trying to find right hand side.
I forgot, but I remember doing it.
I like it. That's a perfect answer. Basically, we find something called the force equilibrium. So you find all the internal forces in the beam, including the steel, compressive steel, tensile steel, and compressive concrete. And we have to find for something called DN, right? And you can find DN using the force equilibrium. So that's just a matter of summing all these forces together, right? So these forces going to the left is equal to the force going to the right, essentially. That's what it means. And then you'll have this unknown called DN, which you solve for. And if you have fucking compressive steel, it'll be quadratic. Because if it's not equal to FSY, you're going to have problems because it's based on the strain in the concrete at that particular point. And so this is a quadratic function, essentially. Then you have to check whether your assumptions are right. So you need to check if your compressive bars were less than the steel strain limit. And you need to check your tensile bars are greater than the steel strain limit. Then you have to calculate the moment, the sum of the moments around the neutral axis. So that's the reason you needed DN, right? You needed DN because you needed to find where this point was so that you can take the moments about it and calculate the lever arms and stuff like that. Okay, pure tension. Here's our last one. Who's next? Because maybe Arjuna. Okay. So, what do we know about concrete and tension?
It's pretty shit.
Perfect. I like that answer. So, what do you just without? I mean, you can look at the screen for hints, but what would you assume the tensile, pure tensile properties of this column are? This reinforced concrete column are, based on your understanding that concrete's useless in tension. Would it be 0 or would it be higher than 0 for its tensile capacity?
In a pure tension environment.
Yes. So everything's being pulled in tension.
Surely it's just above 0 still.
Why is that? You're right, but why is that, do you reckon?
Because even though it's pretty shit, I feel like concrete off fives again. It has some
It has potential.
based on the strain diagram, it does have at least a little bit of component that is affected by tension.
The concrete itself. Okay, think of it what's a good thing to think about? Fuck. Think of it like bread. You know, crusty bread. Concrete's kind of like that. It's brittle, right? So if you pull it, it'll have very minimal tension. In fact, in the standards, we consider it 0 because it's literally so little. And you're right in thinking that it does have a little bit of strength, but it's not due to the concrete. It's actually due to the steel.
Mm-hmm.
So all of the tensile force in our calculations is purely attributed to the steel. Oh fuck, I drew that wrong. It's just the area of the steel, like the compressor bars and the tensile bars, and you multiply it by the yield strengths, and that's it. That's all of our tensile strength that we consider. We don't consider any of that, like that concrete's actual tensile strength. Yes, you're right. It is a little bit like how bread has a little bit of tensile strength.
Yeah.
I'm thinking of like a baguette or something. But like that's like so minimal that like you don't even consider it. It's if fucking the bread had like tensile steel bars inside. You know what I mean? That's the tensile force you're actually considering.
Radio.
Yeah. Yeah, that's the end of my yap. So yeah. Do you guys have any questions?
Is the recording stopped yet?
I'll stop it now. Do you want me to stop it?
Yeah.